Okay, let's get started, everyone. Let's see. Move this up. All right. So it is April 24th. And what are we talking about today? We're going to keep talking about, yes, we're talking about compilers, but we are going to talk about parsing continued. We're going to talk about our top-down parser, sort of like what we were seeing before. We're going to talk about, sometimes it works very well, and it especially works very well if we make assumptions, but as we start reducing the number of assumptions that we make, we see that it starts to break in interesting ways. And so what we're going to do is we're going to have this interplay between the parsing algorithm and our grammar. And I know like in the previous few lectures, we kind of said, your grammar is something you write. You can kind of have your non-terminals. Those are like variables. You can do what you want with your grammar. But what we're going to see is that in order to get good top-down parsers to work, sometimes we have to massage our grammar a little bit. So today we're going to be looking at how we can rewrite grammars to avoid left recursion, which is essentially part 2 of your homework. And then we're also going to talk about how we can analyze those grammars and get a few special sets called the first set and the follow set that will help us write even more efficient parsers. Okay, so as always, let's start with some announcements. So homework 2, I decided to extend the due date to Monday. I know there's been a little bit of friction with AutoGrader, so I appreciate people posting Piazza posts. There is an issue right now that's stopping it from checking the ambiguous grammars, so that's going to be fixed by the end of today. Today we looked through a bunch of test cases and we looked through that. So by the end of today, the AutoGrader should be fixed and be giving more meaningful results. Like I said, please help us out. Please post on Piazza, and we'll get this all sorted out. We're working on this together. I know like there might be some frustration, but last year this assignment was basically a paper pencil assignment, which can be nice, but it makes it really hard to test your grammar. Like last year, if you did this, if you wanted to see if a string matched your grammar, you would have had to try to draw your own parse tree, and people ended up being very confused about what strings got matched or not. The nice thing about Ply is, number one, it gives you experience using a parser generator. This is probably the tool, like a tool that you will use if you write compilers, in your job or in whatever you do after this class. So it's good to get some experience using tools like that. And the other thing is you get to experiment with your grammar. You get to write a string and say, does this get accepted or does it not get accepted? So it makes everything a little bit more interactive. I know that there's some friction, but we're working on it with you. And like I said, we'll make the due date on Monday, so hopefully that helps you out a little bit. For help and for any issues, just ask on Piazza. Like I said, no guaranteed help over the weekend or off business hours, but we'll do our best. And there's we'll also answer some questions about the homework coming up in a sec. But one of the common questions we're seeing is that do you have to return anything from the parser? And right now, I do need to double check because I think Max posted on Piazza that the default is not to throw an exception. So I'm seeing that the default is to throw an exception if you run into an error. But we'll work on that and figure that out. But your parser at this point does not need to return anything. You're just checking to see if it matches a string or not. And as a result, if it returns none, then that means that you made it through the parser, you made it through those production rules. And even though you're not returning anything, the fact that you made it through them means that behind the scenes, it was able to implicitly build a parse tree and match your string. If you make it into the p_error, that means that somehow it didn't make it through those parser rules, and then you didn't match the string, and that should technically throw an exception. So we're going to make sure that works for everyone. Okay, I do have a part in the slides where we can answer some more questions about that, but I do want to go through a few more announcements. So please just make sure to use private posts on Piazza for any questions, especially related to grading. We have been getting some emails, which is I want you to contact us, but inboxes tend to be pretty chaotic, and it's nice to have everything in one place. So private posts on Piazza are the best way to make sure who needs to see your post actually does see it. So let's keep that in mind. The other thing is that we have the midterm coming up in, let's see, it's not this Monday, but it's the Monday after that. So I promised everybody a little bit of a study guide. I do want to say, though, that any of the following are fair game. That's on the following slide. But I also want to say that anything not listed below, but anything that was that we went over in the lectures. That's also fair game, but I think I did a pretty comprehensive review. But I also want to mention that any combination of topics or any sort of problem solving related to the topics is fair game. You know, it's not just going to be memorize what's in the slides. It's going to be like, do you understand the concepts? And you know, like I said, this study guide is basically what we've looked at so far. So nothing on here should be surprising. We studied regular expressions. We looked at operators like star, union, concatenation, how to specify them, how match works versus full match, those things. We talked about scanners. We talked about what the scanner API is, like .token, and what token returns. It returns a lexeme. And so if given token definitions and an input string, are you able to tokenize it and return the lexemes? You need to know how to specify tokens and how to specify token actions. Lately, we've been talking about grammars. You need to know how to specify grammars in this BNF form, where you have terminals and non-terminals. You need to know how to identify and avoid ambiguous grammars. You need to know how to show a derivation for a match or a parse tree to show a match. Today we're going to talk about how to rewrite grammars, not to be left recursive, so you need to know that. Also the first plus sets, so we're going to talk about that in class and also in the homework. And also know how the top-down parsing algorithm works. We're also going to talk about another algorithm called recursive descent. We'll either get to that today or on Friday. We'll also talk a little bit about symbol tables. So we'll talk about those. And then I do believe we have 2 lectures at the beginning of Module 3, and they are fair game as well. So hopefully you see there's nothing in here that's a surprise. We've gone over examples in class. We've gone over examples in homework. I'm not reaching into the book or anything. It's just kind of everything that we've been talking about. Yeah?
So next week's lectures will also be covered on the lecture?
Yeah, everything inclusive, but you know, I tend to be reasonable. I'm not going to give a super hard question on module 3 if we just have the first 2 lectures on it. Yep. It's going to be weighted more towards the stuff that you've had time to study and practice in the homework, which is basically this. Yep. Yep.
Sorry, what day is the midterm planned for so far?
May 6th. Yep, Monday. And you're allowed 3 pages of notes, front and back. I try not to make these memorization tests, but I also don't want to give you 10 pages of notes. Otherwise, you'll spend all your time taking notes and not learning the conceptual components. Any questions? Okay. Cool. Let's talk a little bit about the quiz. So the first question on the quiz, which hopefully you're getting some practice in the homework, is which of the following can be sources of ambiguity in grammars? So can associativity be a source of ambiguity? Who says yes? A few people say yes. Anybody say no? Right, so associativity can be. Remember, that's when you have like an expression minus an expression. And if you have that parse tree, if you have that choice of whether to recurse down on the left side or on the right side, that's going to give you ambiguous. It's going to give you 2 different parse trees. And whichever one you recurse on, whether it's on the right side, that means you're going to basically go evaluate it from right to left. And if you recurse on the left side, that means you're going to evaluate it from left to right. What about incorrect parentheses matching? Is that a source of ambiguity? Who says yes? Who says no? Yeah, I'd say this one's more like no. It's, your parentheses matching is just part of the grammar. It doesn't really, as long as they fit into the grammar where they belong, they're not really going to lead to ambiguity. What about precedence? Is that a source of ambiguity? Did we talk about that? Yeah, who says yes? Yep, that was the first one. You should kind of have that drilled into your head. And what about operator commutativity? Is that a source of ambiguity? We talked about associativity. When I think about associativity, I also usually think about commutativity. Can anybody remind us what commutativity is? And does it make a difference here? Max? Yeah, so if you have A times B, does that equal B times A? Of course, with not including auto capitalization. Yeah. So, yep.
Really, associativity would be if you have 3 numbers and you can't evaluate, and you're all subtracting, you can't evaluate the back right before the left.
Right. Associativity is kind of like how you evaluate it, like left to right.
You're not changing the order, it's the order of which you're evaluating. Yeah.
Exactly. So they look similar, but they are subtly different. And there are operators that are associative but not commutative, and vice versa. But yeah, so commutativity is if when you swap them, when you actually swap the order. Turns out, we will talk about commutativity when we talk about compiler optimizations. But when we're parsing, we generally don't worry about swapping ID order in an expression or anything like that. So commutativity actually doesn't really show up in parsing. It does show up in optimizations, and we'll talk more about that when we get there. So the answer here is associativity and precedence. Those are sort of the two classic ways that ambiguity can kind of sneak up into your grammars for expressions. Okay, now the next question was, hopefully, you didn't really have to write anything, but my hope was that you downloaded Homework 2 and got started and started playing around a little bit with Ply. So how many people have done that? Decent amount. Okay, like I said, this is a new homework assignment for us. I mentioned before, there's going to be a little bit of friction, but hopefully it's an interactive experience for you. We're trying to make this better for both of us. But let's talk about it. Do people have questions as it is? We talked a little bit about before, but how are people finding it? Working with Ply. I'm seeing some thumbs down back there. Yeah, working with any framework can be a little bit difficult. Yep.
I guess just where it slowly started to lose me is it wasn't the lexing document, it was the parser document implementing the p term, p expression, that kind of.
Yeah. So those they're implemented as doc strings, and you sort of write your production rules as doc strings underneath those functions, right? And that's it can be a little bit of a strange specification. Yeah.
I think it'll just take some time to get used to.
And start small, because these things, somebody asked on Piazza, how do you debug these things? And it turns out that it's really hard, because they take your production rules and they transform them into very complicated algorithms. We are talking about the easy algorithm. There is more complex algorithms for parsing that Ply does behind the scenes. And so you don't want to reach into that machinery. You want to do it like black box debugging. You want to specify simple rules, try sending inputs through, see if it matches when you think it should match, see if it doesn't match when you don't think it should match. And you can start off by having ambiguity in your grammar. That could be a way to start off, just to make sure that you are making it through those production rules. Then you can make it more complicated as you go through. But just take it step by step, black box debugging. This is an advanced computer science class, and this is kind of how the real world works with a lot of these frameworks. So I think it can be a little bit difficult, but it's good practice for these sorts of things. Yep.
I'm wondering, is Ply used in industry? Is this a popular framework?
Ply, I don't think Ply would be used in industry. Ply is basically a Python implementation of Lex and Yak, and those are used in industry, although they are very old. The more modern ones, and I was talking about this a little bit earlier, there's things like Antler. Rust has some really good ones. The thing is if we were to talk about those end up being much more complicated, because parsing is complicated. There's many more corner cases. There's many more syntactic sugar to do. And I imagine, in my experience, if we used one of those in these class, we would have most people giving thumbs down when I asked how it was going. So Ply in my experience, it tends to be one of the more friendly ones. I use it in research when I need to quickly roll out a compiler, because it's straightforward, it's simple, but there are lots of other ones. In fact, even back when Yak was made, do folks know what Yak stands for? It's a nice animal, but yeah, Max. Yes, Yak stands for yet another compiler. So even back then, there were many frameworks for this, and that exists today. I do my best to find the most friendly one that plugs into, kind of what we already know and are using. Okay. Any other questions? Any other experiences that people? Yeah, Alex?
I guess, the first stumbling block for me was in the parser method definitions that it was all doc strings and I wasn't actually writing functions.
Yep.
Once I got past that part, I essentially just had to think of how does the CFG work, and then the framework kind of just fell into the background of what I was doing. So
Yeah.
it just took a second to just okay, I'm not writing a function that returns something or does something.
Yeah.
This is just the stand-in for the way my CFG is displayed, and then after that, it's a straight shot.
Exactly. You're not really writing a lot of Python code. You're writing grammars as doc strings for functions. And the Ply documentation goes over that. We provided some beginning points for you. So, I'd say, I extended the due date to Monday. Have a look. Get started. poke around at it, even just to get the hang of things. And like I said, there was an issue with the autograder testing for ambiguity. That's going to be fixed by the end of the day. Another thing is how do you test this? Like, people, you're going to write your grammar, and then, like I said, one of the big benefits from last year is that you actually get the chance to test this. Last year, you would have just, had a paper and pencil and had to draw parse trees. What are some of the strategies that people are thinking about for testing this? Yep.
Have test files of this, whatever part of it you're making now, and see if that can successfully parse that.
Yeah. I would say look at that programming language specification that's in the document and think about what type of programs we're accepting. They're going to look very close to C. We don't handle all of C, but they're going to look very close to C. And then start simple. Start with int I semicolon. Can you handle that one? Try an if-else statement. Try that one. And just slowly build up. Now, one thing about this part of the class is that you're sort of responsible for testing this yourself. Of course, we have test cases that we're going to run, but at some point, again, this is an upper division computer science class. When you look at C++, C++ has a language specification. It's thick and it's not the most friendly thing, but if you want to know if a program is valid in C++, somebody has to go read that and then translate it into a program that is actually accepted. Compilers is the study of that. So coming up with your test cases, going from that PDF specification to test cases that your compiler should accept, I would say that's a big part of this class. This class isn't just about writing grammars and stuff like that. It's about reading grammars and understanding what the programming language should be. And when you eventually get to design your own programming language, you can decide how to write it down in English so that people can try to understand what it means. And it's this is just an exercise in sort of that whole process. Whereas I think a lot of other classes, or if you're used to leak code, it's like, here's a specification. We're going to give you a ton of inputs. No, part of this class is identifying what those inputs should be, what is correct and what's not. And some of it is, some of it you'll scratch your head and have to think about, and hopefully you'll get an appreciation for, the people who build languages like C++ and build languages like Python and try to describe them in docs, because as I know, and our specification isn't perfect either. You might find bugs, but it's a lot of what you're going to be doing in the real world, especially as you learn new languages. Python was barely around when I was at university. I never took a class that taught Python, and you just have to learn languages by doing stuff like this. So, hopefully it's a good learning experience. And I don't mind on Piazza if people talk about individual test cases. If you kind of say, is this allowed? Is this disallowed? Please don't upload bulk test cases, but I think it's actually a good experience to talk about individual test cases. And in fact, people still do that to this day with Python, C++, and especially GPU languages, because nobody can seem to agree on what they actually do. So yeah, I think it's part of a compiler's course to experience some of that. Yep.
Can I ask a specific question about the homework?
Yeah.
So for the if-else statements, it says it's just if followed by an expression enclosed in parentheses, followed by a statement. Does that statement have to be in brackets or braces as well?
So yeah, does that statement have to be in braces? What do people think? Yeah.
We have for Fridays, I have a separate block statement. So it's like a L brace statement and a R brace.
Yeah.
And that's what I use to deal with whatever.
Mm-hmm.
Like if left parentheses, expression, right parentheses, and statement, the block just takes care of the brace.
Yeah. So that's exactly right. A statement can be a declaration statement, or it can be an if statement. Or a statement can also be a compound statement, which includes those braces. So an if followed by a statement, it can include those braces, but it doesn't have to. Yep. And I think that's an interesting way to think about programming languages, because now when you think about something like C, that's the same way C is specified. A statement is either a declaration, or you can have a compound statement. And that's why in C, some of you don't know this. I didn't know it for a while, but you can just put braces anywhere in C as long as they're matched. It's because they're a statement, so you just throw them anywhere. Yeah. Good question. Anyone else? And I think these are the sort of things that are important to discuss. Like, we should be looking at the specification and thinking about these sorts of questions. Okay, well, start working on it, and happy to have discussions on Piazza. Or if you have questions about Ply, if you have questions about the autograder, or if you have questions about what should be accepted or not. I think they're all good discussions. James?
Is there a time when you might use braces without like an if or a keyword before it that would help with maybe precedence or something?
Yeah, what do people think? Have you ever seen a case where you use braces without like ifs or whiles or for? Simon?
I know in C it can be helpful for scope. So I guess this isn't completely correct, but within like switch cases, inside of the cases, all the variables are in the same scope. So it's sometimes helpful to do like braces around those.
Yeah, so scope is the one that I would think about, but yeah.
Sometimes I just use it for like organization.
Organization's pretty good because, especially if you tab in, right, you're kind of like this section does this section does this. We're going to see scope come back with symbol tables because we're going to kind of see braces used in interesting ways that way, but yeah.
So if you use it for organization, you have to be aware of the scope because you might do something with variables.
Yep, exactly. And you have to make sure that you don't need anything, that anything you declare within those braces you don't need afterwards. But yeah, for scope it can be interesting because like you can have something like int x equals 5, and then if you open brace, close brace, you can have int x equals 6 or whatever, and then if you print x, it's going to print 6. So you basically make a new scope. You get your closest declaration there. And so one thing is like sometimes if you're declaring multi-line macros, like macros are things that just get copied and pasted in, right? If you want to use a temporary variable, use braces, otherwise you could potentially clobber the scope for somebody else. And yeah, so that can be a good place to use them. Yeah, good questions. And I do think, studying compilers is where we start to think about some of these design decisions and where they might be useful and interesting. All right. Anything else? Cool. If not, let's see. Zeph asked for an example. It doesn't look like they're here, but I think it's still useful to go over this. What I want to do is, people were asking kind of how an extended parse tree looks for a relatively large grammar. So if you remember, we did this grammar for regular expressions. We did this before we learned how to completely disambiguate it. But remember, we had the choice or union operator. In this one, we used an operator for concatenation. We had dot, just to make sure that we had an operator for it. We had the cleany star, and we had parentheses. So as a review, remember, when you do this, and you will be doing this in your homework, come up with your table. Your table goes operator precedence from lowest precedence to highest precedence. Then you give them each a name. So for example, at the top here, we're going to have union. We're going to have concat, starred, and unit down here. And then what we do is the productions, because these are left associative, you recurse on the left. You say left, operator, and then your right-hand side is the component that's one level down in the table. So concat or concat. And then down in concat, again, because it's left associative, we do concat dot starred or starred. Star is just star, star, or unit. And finally, you can restart the precedence with parentheses. Now, if we see how the parse tree looks, there is only one parse tree that we can get for this expression. This is a regular expression. And, thinking about how you do this, we're talking kind of about algorithms, how to implicitly do this top-down parsing. But how you would do it, there's not a real algorithm. Some of it is kind of trial and error. But one thing you can do is you can say, I need to match this pipe operator somewhere. There's only one place that I can match pipe because there's no parentheses. Because there's no parentheses, we're never going to restart our table. We just need to drill down. So because there's no parentheses, we need to match pipe somewhere. The only place to match pipe is in a union. So union's going to be our top level. That's going to allow us to match pipe. And then that's going to give us a union or a concat. So we have a union. This is a union or a concat over here. Well, no more need to match union, so that union can just drill down and become a concat. And then we need to match that dot. So that concat is a concat dot star. B becomes a star, but there's no star there, so star can just go down to unit and become a character. And then concat over here, again, there's nothing else to match. There's no star or concatenation operator, so it drills down and becomes a star, unit, and character there. Like I said, when you have these tables, and again, this is a simple table. C++ has like 15 levels. You tend to get these long sticks at the end because that's how you end up turning into your base case, which is a character here. In the case, yep?
Maybe I'm confused on the right. It goes, would it be starred unit, or would it just be starred unit?
Right here?
Yeah.
Let's see. So starred, and you are right. Like I said, this is why it's nice to have a tool like Ply, because drawing these by hand, yes, end up missing things like this. Good catch. And yeah, these just become long sticks at the end, and it's easy to forget one. But yeah, so starred becomes a starred star, and then the next star becomes a unit, and then a character C. So that's kind of how you take a more complex expression and get your parse tree. If we had had parentheses somewhere, it gets a little bit more deep because you'd have your union. Your union here would basically need to drill down. This union would need to go to concat, to star, to unit, and then that unit becomes an L-par, R-par union, and then that union becomes a concat. So basically you'd have a very long stick here making that round trip from union all the way down to unit, back up to union, and then to concat, which would eventually match that one. So parentheses, if you put them where they're not needed, it's still valid, right? You can put parentheses wherever you want, but you end up, that would give you long sticks in your parse tree. Yep?
So does the whole expression start out as one union, and then from there our grammar takes over parsing it out?
Yeah, so when you do the table, what we kind of have is an implicit that your start symbol is a union. So you have to start as a union, and that's so that you can potentially match a pipe, if there is a pipe there, and that's going to be at the top of your tree, which has the lowest precedence. Whatever's at the top of your tree gets evaluated last.
And if there's no pipe, it's like, oh, then it doesn't need a pipe, so let's look at concat and see what it needs from there.
Yep, and just drill down, continue drill down. Yep. Any other questions? Okay, great. So that was an example of that. Let's talk a little bit about what we were doing last time, because this will be important for the new stuff we want to do today. So remember, last time we were talking about a top-down parsing algorithm, and this slide's a bit busy, but now that we've had a chance to think about it for a day or two, remember the algorithm. We basically start with our start symbol. So our start symbol in this case would be expr. If we were up here, our start symbol would be union. This is basically the intro to our grammar. And then our focus is essentially the symbol that we are looking at dealing with, whether it's a non-terminal or a terminal. So to start off with, our focus becomes the root. It's just the start symbol. We have a stack. This is basically the work that we need to do. These are all the symbols that we need to deal with is on the stack. And then we have our lexer. Our lexer tells us the next thing that we are looking to match. And we get that with the token function. Remember, that returns the next lexeme. That's what we need to deal with. And then essentially we need to iterate. I just have a while true here because I think it's more convenient to case it out. What we are going to do is we're going to iterate until we have toMatch equals to none. Remember from our lexer, if toMatch is equal to none, we are done lexing the string. There's no more tokens or lexemes to deal with. And our focus equals none, which means there was nothing left on the stack. So that's sort of our end condition, is that we've lexed the entire string and there's no more symbols for us to deal with. Now, the more interesting stuff happens when there is a symbol for us to deal with. And while we're looking at a non-terminal, so if we're looking at an expr or a unit or an op, we need to pick which rule to expand. And in some cases, and you'll see this in your homework, if there's only one option, maybe you have a production a non-terminal that has just one production option, then you pick that one. In this case, all of our non-terminals have two options. So for expression, you can pick 1 or 2. For unit, you could pick 3 or 4. For op, you can pick 5 or 6. You have to pick the next rule. And once you pick that next rule, you push the symbols onto the stack. If you pick rule 3 as a unit, then that means that when you pick that rule, you are saying, I need to match an open parenthesis, I need to match an expression, and I need to match a closed parenthesis. So you push those onto the stack. That's what gets pushed onto the stack, and then your focus becomes the top of that stack, which, if you picked rule 3, that becomes an open parenthesis. So that's what happens when you're looking at a non-terminal. You're basically making the choice. You have to make the choice of which rule to pick to expand. Now, if you're looking at a terminal, for example, if your focus is an open parenthesis, then what you do is you just look at the lexer. You say, what did I need to match? And if you are what you need to match, then you just get the next token that you need to match, and you pick the next thing to focus off the top of your stack. So essentially, this is doing a left derivation. Whenever you reach a non-terminal, you just pick the rule to expand, and you just keep pushing stuff onto your stack. So, like we said, oh, sorry, Laura? The focus and to match. So right now, in the way that we have it, we're assuming magic. We're assuming that this rule always picks the right thing. And if this always picks the right thing, and if we are going to accept, then focus would equal to match. We are going to start peeling away that magic. And when we peel away that magic, this might not always be true. So what we're saying here is we need to make sure that if we have a terminal, like a parenthesis, we need to make sure that's what our lexer told us that we needed to see. Yes. So right now we are assuming that it's always going to be if we assume that we always can match the string, and if we assume that we always pick the rule, then this will always be true. Yep. So, but we are going to slowly take a step back from those assumptions, because that is a big assumption that we always pick the right rule, right? Yep. And then I saw another hand. Yep.
Yeah, but just to clarify, right now this algorithm isn't actually constructing a tree, returning to
No, this doesn't build the explicit tree.
So it's just verifying that it's
Implicitly, there are ways to squint at this, and it is essentially doing a post-order traversal of a tree. You can think about it like that, because every time you pick a rule, that's like drilling down a level, and every time you match, that's like a leaf node, and you pop up the tree, because you're dealing with a stack, right? So you come down, you pop up, you go down, pop up. There's a way to add print statements here that you would essentially print the parse tree. Yep, good question. Laura? Yep, so this is, again, there's a lot of magic here, and we are assuming that we are going to accept it, and we're assuming that we always pick the right rule. Yep, and we are going to take away some of that magic today. All right. Good questions. Okay, so let's talk about some pathological things that might happen. So if we don't have a magic choice, and if we kind of look at these production rules, and this is a little bit of me asking you to read my mind, because there's a lot of things that can go wrong, but I'm thinking of I'm thinking of a very specific thing that can go wrong here. If we're not able to always pick the right rule, and if we have to expand, can anybody see something here? When you write a recursive program, what do you always need to be aware of? Yeah.
I think the rule starts with the same thing as its name, then it would just kind of keep looping forever. There's no base case. Yeah. How many of us have written a recursive program but forgotten the base case or gotten the base case wrong, and it just goes forever, right? So yeah, what happens here is, if our start symbol is expression, and let's say we pick rule. I think we just pick rule 1. I think this is off by 1. But yeah, if we keep our focus is going to be expression,
And then we can just say, hey, I'm going to expand expression to rule 1. I'm going to expand expression to rule 1. I'm going to expand expression to rule 1. And keep going. And then our stack will eventually, we'll just keep pushing that onto the stack. We can pick the next rule, keep expanding expression to itself. And, this is essentially infinite recursion. So we don't want infinite recursion. We want to have base cases. So I wish there was another way we resolve this magic, but what ends up happening is that top-down parsers, they cannot handle left recursion. And what do I mean by left recursion? I mean when you have a non-terminal and there is a production option. So one of the choices that you have refers to itself. So that's called direct left recursion. And the reason for that, is just think about it like a recursive program. If you just always pick this rule and say, I'm going to choose an expression. Well, an expression is an expression op unit. I'm going to expand that expression to an expression op unit. You keep going forever. That's called, direct left recursion because it is the leftmost non-terminal is the same as the non-terminal. I mean, this is a valid grammar. You can give this to Ply. Ply will happily eat this because Ply is not a top-down parser. But for a top-down parser, we cannot have this. We also can have indirect left recursion. What that means is, maybe, because a grammar is something we write ourselves, maybe we say something like an expression base can be a unit or an expression with an op, and an expression with an op can be an expression base op unit, and that expression base can jump back up to expression base. And so sort of you go expression base, expression op, and you sort of have this indirect recursion. But that's still just following that leftmost symbol, you can sort of get into these recursive cycles. We cannot handle those. So we rely on a nice property of context-free grammars. And that property is that any context-free grammar can be rewritten without left recursion. And what's even nicer is there is a recipe for us. And let's kind of look at that recipe with an example. If we have this grammar, we just have phi, and phi is either phi followed by the character A or B. What does this describe? What sort of strings are this? See, does it accept B? All right, what were you going to say?
I was going to say it's B followed by at least one or more A's.
Let's see, B followed by at least one or more A's. Yep, that's exactly right because, eventually, you have a B here for phi, and then you have at least one A, but you can kind of recurse and make as many A's as you want, as long as you terminate with a B. So that's exactly right. Okay? So is this left recursive? Yeah, because we have an option where we can take the leftmost rule is our production, is our non-terminal, sorry. So if we wanted to write this, and this is a recipe, you can make a new non-terminal. So I always just call it phi2. And then how you break this up is you say phi is equal to B followed by phi2, and phi2 is A followed by phi2, or the empty string. Okay, does this make sense? Now, what we can do here, sorry?
What keeps us from infinitely recursing the other way now?
This one?
The phi2. Like, if you B phi2 and then A phi2, why don't you just keep selecting A phi2 over and over again?
Well, see, this is where it gets interesting, because in order to select A phi2, if we go up to our algorithm, you're going to have a terminal, and that means that you have to make progress in your lexer, right? Because you have to get that token. You have to say, I match that A, and then I can recurse, and then I match that A. So at least you're eating one character at a time in that string. Like you're making progress. You're not just recursing.
Growing, he's eating off the front A before going.
Exactly. So you can make it super deep, but you are going to terminate because you are eating a character every single time. And that's the key point here, is that before you do a recursive call, you are making progress by eating a terminal. Yeah, does that make sense to folks? So what that does is that little example with the characters A and B, it generalizes. So what we're going to have is we're going to have some grammar, and it has some non-terminal, and there's a left recursive call, and it's followed by something A. So A can be any sequence of non-terminals and terminals, and B can be any sequence of non-terminals and terminals. And you can just rewrite that by making a new production or a new non-terminal where B is followed by phi2, and then A is followed by phi2 or empty string. So we can actually do that with our little expression language. Here we said there was a problem because we had left recursion. Expr equals expr op unit or parentheses. Our left recursion is right here. So if we rewrite this grammar, we just follow this recipe. So I'm going to make an expr. I'm going to make an expr2. And if we want to say, if we want to follow this recipe, what is A in the case of our grammar here? So our left recursive symbol is here. We have A. So A is going to be op unit. And B is going to be what? Unit. Because here we have, imagine this is expr. A is anything that follows expr. So op unit, A is op unit. And B is whatever is the next production option, which in our case is just a unit. So if we have A and B, our new grammar, which is exactly the same, and again, you're going to specify this and you're going to want to test it for your homework. Your expr is going to be B, so B is a unit, followed by expr2, right? So this is just following that recipe, except we've substituted where A and B are, and we're substituting phi for expr. And then expr2 is A, which is op unit or expr2, or empty string. Okay, so now we've rewritten this little expression language to avoid left recursion. Hopefully you agree with me that there's no left recursion in this new grammar. Is that right? Because there's no left recursion, we can't get into this sort of infinitely recursing without making some progress. So we have our new grammar up here. It's no longer left recursive. And now when we pick our next rule, no longer infinite recursion, the question is, what happens if we pick this rule 3? This rule 3 is empty string. What that basically means is that we don't have to match anything. So, we don't really have a token for the empty string. What do? Well, if our next rule is the empty string, that just means pop one off the stack. That's all what we have to do. We just pop one off the stack and keep going. So we can pick this rule, and that just allows us to kind of say, all right, go match the next symbol that you have in your stack. So we are adjusting the algorithm a little bit at this point. Okay, so we've kind of taken care of the case where we might have infinite recursion. I do want to talk a little bit about how to handle indirect left recursion. So here, remember, we kind of had this kind of silly case where we said we had an expression base, which is a unit, or an expression op. An expression op can be an expression base, op unit. And you can't really trick left recursion this way because expression base could go to expression op can go to expression base, and it's just a roundabout way to get left recursion. This still isn't allowed. So if you see this, or if you have this in your grammar, you do still have to get rid of it. And the way that you get rid of it is, imagine function inlining. If you have some like C code, you basically need to take this instruction op, you need to substitute it into an expression base, and then what that does is it gets rid of the indirect left recursion. You've just inlined that that non-terminal, and now you have direct left recursion, and then you apply the recipe. Luckily, I don't think your grammars that you will write for your homework have indirect left recursion, but essentially the idea there is you just inline until you make it direct left recursive, and then you apply the recipe. So it's always possible to get rid of left recursion. Yep.
So with previously the way we were talking about, like from a kind of like a tree perspective, I guess,
Yeah, the trees start to look a little bit weird so that's why I think the grammars are really nice to start out with in a way that is left recursive. Like it's a very natural way how to do expressions and stuff like that. When you eliminate left recursion this way, your tree will keep them the same meaning. You can still do a post-order traversal because you still go down on the left. But yeah, sometimes you'll match the empty string, and it is not going to be completely balanced because, let's see. Let me go up here. When you get rid of left recursion, you're going to kind of have this, like one of your nodes is going to have like, an expression 2 is going to be an operation followed by a unit. And I know we like to see nodes that are like number plus number. We kind of lose that structure, but we keep the post-order traversal meaning. And we are going to see examples of the trees that come from this when we make it into the next module. But you're right, we lose sort of some of our tree structure that we might like, but what it does is it makes it possible for us to use these simpler parsing algorithms. And I've said this before, computer science is a study of trade-offs. Behind the scenes, Ply uses a much more complicated parsing algorithm, but it can handle left recursion. We're using a simpler parsing algorithm, but we have to get rid of left recursion. And you can read about those more complicated algorithms in the textbook. I find they are little bit difficult to get into. But good question. And we're sacrificing some of that. Yep.
Can you repeat what you said? Computer is a science or something?
Yeah. Computer science is a study of trade-offs. You're always, if you sacrifice something, here we're sacrificing our tree structure to use a simpler parsing algorithm, whereas you can keep left recursion and do much more complicated parsing algorithms. Yep. And that's not true. Sometimes, occasionally in computer science, you get things for free, but not often. All right. So, yeah, if you have indirect left recursion, which basically means you have to travel through a couple of non-terminals, but eventually you still have this cycle. Essentially, what you need to do is inline. I just have this in the slide so that you can see that it is possible in every single case to get rid of left recursion. You probably won't have to do this in the grammars for your homework. And?
So basically, we're bubbling down from the left side of a production rule that's X per base, and we're looking at the leftmost thing in all of the remaining rules. So we're bubbling up.
Yeah, and in fact, the algorithm to detect left recursion is essentially to make a graph where you just connect, where these are your nodes, and you just connect them based on their leftmost options. And then if you see a cycle in that, that means there's a chance to get stuck in infinite recursion. Yep. OK, so yeah, these slides just show that you inline indirect left recursion. It gets a bit messy, but like I said, I don't think you have to do this in your homework. Point is it's always possible to eliminate left recursion. And in fact, there's recipes for it. And there are some of these parsing tools that will automatically get rid of left recursion for you. So it is possible. So let's kind of see what we can do with our parsing algorithm now. We no longer have infinite recursion. But what we can do is, like, if we have this simple grammar, so this is just a very simple ID expression 2. We can do a plus or an ID, basically. Very simple grammar. But at least we don't have left recursion. So if we want to match just a single character like A, so a single ID, we have start at expression. What we might do is, we need to first off apply rule 1, because that's the only option. So, apply rule 1, then we get ID expert 2. And so we can match ID. So we'd match ID, focus would be A, we would match A, then we'd be left with the empty string. But we'd be left with the empty string, but we'd need to expand expression 2. We'd have two choices here. We could match plus, or we could match empty string. That's where we have our choice here, pick next rule. Now there's two things we could do. We could pick the wrong rule. We could pick rule, let's see, this would be rule 3 technically. Or no, sorry, it'd be rule 2. And then we'd have ID plus expr 2. We could determine pretty quickly that this was the wrong choice because, we'd match A as the ID. We'd try to match plus. There's no plus here. We wouldn't be able to match that. We'd identify pretty quickly that was the wrong thing to do. So what you can do, and again, here we're going to get rid of some of the magic that Laura was asking about. Every time before you make a choice, you can cache your state. You can basically cache what your focus is, cache what your stash is, or sorry, stash what your stack is. Oh, that's tricky. And cache your lexer. And then when you pick a rule, if you make a wrong choice, you can just backtrack. You have everything cached. You have everything memorized. You can just take a step back and you said, that was the wrong rule. I can apply rule 3, which then just gives me ID. And that was the right choice. So before you make a choice, you can basically take your whole state and say, in case I make the wrong choice, I'm going to leave this behind. I'm going to record what choice I make. And that way I can come back and make a different choice if I need to. And what this does is, like Laura was asking, if our focus, if we have a terminal and that's not what we want to match, instead of just rejecting, we now have other options. If we have a cached state, if we can take a step back and make another choice, then we just backtrack. We pop something out of our cached state that allows us to, erase some of our rules up here and just basically go back in time and try a different choice. So, we now start to have an algorithm where we can backtrack. We can make better choices if we need to. There's a reason I'm not going to spend very much time on how to optimize this. Every time you have a backtracking algorithm, it's never a nice thing, and you always want to think hard about how to reduce the number of backtracking options and stuff like that. But we're not going to spend very much time on that because it actually turns out that we don't need to backtrack. So in the general case, if you write horrible grammars, yes, you do have to backtrack in the general case. But in many cases, especially for programming languages, you can get away without backtracking. And let's think a little bit about how that might be. So here's that exact same scenario that we had. We're trying to match A. So we start with expression. We only have one choice there, so we expand that with an ID and expression 2. So now, let's say that we are at this point in the algorithm. We've matched the ID to A. We need to make a choice on expression 2. We can choose 2 or we can choose 3. Can we actually make a better choice here? Because we've already matched that A, our 2 match, the next thing that we want to match is none. We don't have anything else to match. Can we make a choice by looking at this production? Basically, we have these choices, 2 or 3. Is there a way to make a smarter choice here? We know that we don't have anything left to match. What do people think? Yeah.
We match with rule 3.
Yeah, and why is that?
Because we don't have anything left to match.
Exactly. This is exactly what we're trying to match. None goes to empty. We don't have a plus, right? Like if we wanted to match a plus, then we'd want to pick rule 2, right? And what's nice is rule 2 just has a plus right there. So these rules are telling us something. And we should be able to look at these rules and use them to help us figure out how to make a more intelligent choice. So to do that, let's actually define what we call the first set. And so again, you'll get some practice doing this in your homework. Now, I do think this is a fairly intuitive concept. And this only works if you don't have left recursion. And again, it doesn't work in the general case. You can construct grammars where this doesn't work. But luckily in programming languages, we tend to get grammars that are nice where this does work. So for each production choice, so every choice that you have, 1, 2, 3, 4, 5, 6, 7, you define the first set. And the first set is a terminal that choice can begin with. So let's start off with something easy. If we come down here to ops, and let's take production choice 7. The terminal, if you pick this option, if you pick number 7, the first terminal that you see needs to be a star. In this case, it's the only terminal that you see. It's the only thing that you see. But the first terminal that you see if you make choice of 7 is a star. Similarly, if you make choice 6, the first terminal that you see is a plus. It's the only thing that you see, but it is still the first terminal that you see. Plus. if you take rule 5, again, the first, but really the only thing that you see is an ID. ID is a terminal. If you pick rule 4, you can see a few of things, right? Rule 4 is starting to get more interesting because it's an open parenthesis, expression, close parenthesis. But the first terminal that you have to see, if you pick 4, the first terminal that you have to see is open parenthesis. Does this make sense what we're doing? Okay. Now if we pick rule number 3, these empty strings, they get a bit weird, so we're gonna deal with them later, but we're just going to say empty string for now. Now, this one is even a little bit more tricky. If we have 2, if we have expression 2, the first thing that we see is an op. An op is not a terminal. So what we have to do is we have to then go down to op and say the first thing that we see is the union of the first things we can see with op. So if we're going to match an op, the first thing that we can see is a plus or a star. That's why these are sets, not single characters. So this can be plus or a star. Because the first thing we see is an op. The first thing that an op can see is either a plus or a star. And now come up to regular expression. If we do that, the first thing we see is a unit. Unit is a non-terminal, so we need to go and see what our choices for a unit are. Well, our unit are 4 and 5, open parenthesis or ID. So you kind of start with your simplest rules. A lot of times they're only going to be a single character. But as you bubble up, if you see a non-terminal, you have to go and then take a union of every option there. But what the first set basically tells us is if you make whatever choice you make, if you make choice 2, the first thing that you need to match is a plus or a multiplication. So hopefully you can start to see where this is going to be useful. We can use these first sets to decide which rule to pick. So when we pick the next rule, we have that token. Remember, we get that token from the scanner. The scanner tells us the next thing that we need to match. And the first set is going to tell us what terminal we're going to need to match if we make that choice. So just by using that to match and having that first set, that can essentially make that choice for us. So for example, if you were trying to match an op, well, an op has 2 choices. It can be a plus or a multiplication. That's not hard to choose because you know what you need to match next. You need to match a plus or a multiplication. So choosing between 6 and 7 is no longer a difficult choice. If you have something like a unit, that can be an ID or an open parenthesis. You know which one you need to pick because you have that from the lexer. Does that make sense to people? Okay. So the elephant in the room is this empty string because, empty string just basically means you're matching nothing. You just move on to the next token. That's not a very useful thing to have a first set for. So to solve that, what we need is when we have the empty string in any of our first sets, we need to come up with what's called the follow set. So I put not applicable because, technically you can come up with a follow set for every rule, but it's only really useful when you have the empty string as one of the options. So we need to come up with the follow set. What the follow set is we need to come up with whatever terminal we find that can follow this rule, because we match the empty string, which means the thing that comes after, the symbol that comes after that is what we need to match. So whatever follows that. So let's see, what can follow an expression 2? Well, if we look at what can follow an expression 2, we look at expression 2 here. Well, this is at the end. Nothing follows expression 2 here. So, that's fine. That just means we need to bubble up and we say, oh, what can follow an expression 2 here? Well, what comes after an expression 2 here? Well, one thing is expression is the top. So since it's the top, nothing, that's an option. You can have none here. So nothing could follow it. But what else can follow an expression? Because now we need to ask what can follow an expression. Well, what can follow an expression? A closed parenthesis can follow an expression. So the follow set ends up being none or closed parenthesis. So again, the first set is the terminal that you need to match if you make that choice. The follow set is the terminal that comes after you make that choice. So that makes sense when you have the empty string, because basically you need to say what comes after. When you combine them, you get the first plus sets, which is just the union of the first and the follow sets. And what this means is these are now exactly what you need to have to make your choice on the next rule to pick. So what you do is you say, if each non-terminal has a disjoint first plus set, then we do not need any backtracking. So for example, expression has 1. It only has one choice. So of course, these are disjoint options. You'd only ever have one choice. Expression 2 has 2 choices. But because these are disjoint, you have plus